In this video, I am going to go over the explanations to Part C of the August 2019 Chemistry Regents exam. Now, my suggestion would be that you have out at least a piece of paper and a pencil and the reference tables. You try the questions for yourself and then come on back for explanations. Part C is important. It's as important as all the other parts on the Chemistry Regents exam, so I am so glad you're here. Let's get started. As you can tell, from 66 through 68, we have bunches of questions that have to do with reading passages or maybe a balanced equation or a diagram. In this case, you would want to read through the reading passage and then answer the questions. We're going to go right to 66. Explain why the sample in the crucible was heated repeatedly until the sample had a constant mass. Well, in order to figure that out, we have to take a look at that reading passage. We are dealing here with what's known as a hydrate. And as it says, a hydrate has water molecules in the crystalline structure. We would want to heat the sample repeatedly until it has a constant mass because we would be driving off the water. And here you see the formula for the hydrate, magnesium sulfate, heptahydrate, hepta meaning 7. That's the answer for 66. Let's go on to 67. We need to show a numerical setup. What do we mean by that? Well, that means we're going to go ahead and show the numbers in a formula, but we don't calculate the answer. We're going to calculate percent composition by mass of water in the hydrated compound. Where do you find the formula for this? Reference table T. So let's take a look. Reference table T, it's the last table on the Regents reference tables. We're looking for percent composition, and here it is. My suggestion would be to rewrite that or have it open, of course, when you're working through the question. Let's go back. You see that I rewrote the equation, and of course I put in the part, which is the water, the whole thing, which is the hydrate, that's the crystal and the water. Don't forget the times 100. That's part of the numerical setup, and now I got to plug in the numbers. Going back into the reading passage, we had 5.06 grams of the salt, the hydrate, heated, so that is the whole mass. So the 5.06 goes in the denominator, and I need the mass of the water. Now this is where you have to make sure you understand what goes above. The sample was heated repeatedly until the remaining magnesium sulfate had a constant mass of 2.47 grams. If you plug 2.47 in the numerator, the top half of the fraction, you're going to get it wrong because we want to know the percent that's water. So that means we need the mass of water. Well, the 5.06 minus the 2.47 would give us the mass of the water that was driven off. Now, use a calculator to figure that out. And we want to put 2.59 here and percent water. There is my numerical setup. Moving on to 68. In 68 now we're going to determine the gram formula mass of magnesium sulfate heptahydrate. This is a great spot to just show you the difference with the math on the Chem Regents exam. 67 was all about showing a numerical setup but not solving for the answer. 68, now we're actually going to answer this because we're going to determine the gram formula mass. So you're going to put the number on the answer sheet. Your gram formula mass for this compound, here is the formula, means we need to take into account the mass of all the different elements in the formula and the number of times they appear in the formula. Let me show you what I show my students. List all of the elements found in the formula, the number of times they appear in the formula, and then you need to get the atomic masses off of the periodic table. Now your atomic masses, remember, are your decimal point numbers. You can round it to the whole number here. It says nothing in 68 about sig figs, and that's exactly what I'm going to do. So magnesium's 24, sulfur 32, oxygen 16, hydrogen 1, oxygen 16. Now, if you took it out a decimal place or two, that's fine. Just leave it. Now you're going to multiply these out and just add them up, and there's your answer. The answer is 246. You see that I showed all my work Even though I don't have to, I wrote it down all on paper, use the calculator, don't skip steps. This is an easy question to get that point. What students do, however, is they'll try to skip steps, do it in the calculator, not write it down. Make sure that you're very detailed in going through all of these questions. Let's move on. Questions 69 through 71, we have a reading passage. We also have a balanced equation. Let's go on to 69. It says to state in terms of electrons why the radius of the sodium ion in table salt is smaller than the radius of a sodium atom. Well, of course, the radius of a sodium ion has one less electron than the radius of a sodium atom. So one less electron makes the sodium ion smaller. Be careful anytime that you have to explain anything, double check that you did it in terms of what they were asking, and in this case, electrons. On to 70. Identify the noble gas that has atoms with the same number of electrons as a chloride ion in table salt. Well, the chlorine atom has 7 valence electrons. How did I know that? Well, I can look it up on the periodic table, and I know also that chlorine is a halogen. It's in group 17. They all have 7 valence electrons. When the chloride ion is formed, we have chlorine gaining an electron. It moves from 7 to 8. Well, what noble gas is that? Let's go to the periodic table. We find chlorine. It has 7 valence electrons, right? The outermost electrons. I see the number 7 in the electron configuration, or I know from the group number, drop the 1, it's 7. It gains 1 electron. It means it's going to have the same noble gas configuration as Ar, which is argon. For question 70, it just says to identify the noble gas. It did not ask for the name, did not ask for the symbol. It is argon, so either one is acceptable. For 71, for the space in your answer booklet, you're going to draw the Lewis electron dot diagram for the chlorine molecule. This is a diatomic. Chlorine, remember, has 7 valence electrons. So I'm going to draw my Cl, and I'm going to draw 7 dots to represent the 7 valence electrons. Not very well, hold on. When chlorine bonds with itself, it has 7 valence electrons, but it wants to get to the magic number of 8. I'm going to go ahead and show a dash to represent the 2 electrons being shared between them, but don't forget the other electrons in that outermost level. So you have to show those 6 dots, which kind of look kind of funky here, so I apologize, for the chlorine molecule. That's one way. Another way would be that you could show the pair of dots being shared between them, and then all of your dots right around the 2 chlorines. Either way, you have to know that, and it brings up a really good point. You want to practice drawing Lewis electron dot diagrams for the most common molecules, not just the diatomics, but water, for example, ammonia, methane, CH4, carbon tetrachloride, CCl4. There's a basket, I call it a basket of molecules that you have to be able to draw the diagrams for, and then of course some ionic compounds as well. Check with your notes and your teacher, and you can check that out and practice them and be ready for the test. All right, here we are with another reading passage and 4 questions this time, 72 through 75 associated with the reading passage. For 72, state what happens to the average kinetic energy of the gas molecules if the cabin temperature decreases. This is one of those vocabulary words that I talk about a lot. Check out some of my other videos. Temperature is a measure of the average kinetic energy of the particles of that substance. So if the temperature is decreasing, what you're going to say is the average kinetic energy decreases. For 73, once again, what are we doing here? Oh, a numerical setup. That's the numbers without calculating the answer. For calculating the pressure in the submarine cabin if the cabin temperature changes to 293. We're dealing with gases here, specifically carbon dioxide. We have information up here, which goes along with question 73, and I need my combined gas law equation. Where do you find it? reference table T. I'm just showing it to you here, right? The combined gas law equation. You're going to rewrite this on your paper or have it in front of you or on your scratch paper. Remember, pressure and volume units need to be the same on both sides of the equal sign, and temperature must be in Kelvin. If you're given any temperature in Celsius, change it to Kelvin, and don't guess. The temperature conversion formula is right here. I wrote out the equation here, and now we need to plug in the numbers. We got to go back here to the passage. We have an enclosed cabin of a submarine. We have a volume of 2.4 times 10 to the 5 liters to start. And we have a temperature of 312 Kelvin and a pressure of 116 kPa. And then we have to see what's going on the other side. It says calculate the pressure. So we're looking for P2. We're given a new T2 of the 293 Kelvin. However, you don't see a new volume here. Well, and that's because since it's an enclosed cabin, this 2.4 times 10 to the 5 liters is not changing. Do I even need to include it? The answer, of course, is no. If you do include it, is it wrong? The answer is no. Let me rewrite it so that you can see what this looks like. Once you have your setup, you're done. Now that we know the volume isn't changing, you'll notice here with the combined gas law, I just crossed it out. And then I just substituted in the 116 kilopascals, the 312 Kelvin is equal to P2. You want to make that X, go for it, over 293K. You can, remember, leave the volume in. It's going to be the same number on either side. That's fine as well. That's a numerical setup. We're done. On to question 74. We want to determine the number of moles of CO2 at which the air becomes unsafe to breathe, and we're given the gram formula mass. Here, the last sentence tells us as soon as the carbon dioxide exceeds 2156 grams, we have a problem. Well, we need to calculate moles. Let's go to reference table T so I can show you where that equation is. Take a look. You see, here it is. For mole calculations, it's the first equation. You're going to determine the number of moles. Remember, you were given the mass, and in the question, you were actually given the gram formula mass. You don't even have to calculate it. I do want to point out that sometimes students get confused between this equation and molarity. Molarity is defined as moles of a solute over liters of a solution. If you're not sure which equation to use when the word moles is in the question, look at the other information that you're given. It has to fit. In the question that we're dealing with right now, we're given the mass and the gram formula mass. That makes this the one that we need to use. All right, I rewrote the equation, and we're determining the number of moles here in 74. That means we're providing the answer. That's 2156 over 44. Plug it in your calculator, and you're going to get an answer of 49 moles. For 75, we have convert the original air pressure in the cabin of the submarines to atmospheres. Well, the original pressure was 116 kPa. So I need a conversion factor to convert from kilopascals to atmospheres. You don't have to memorize the conversion factor. You can find it on the reference table. Let's do that, and I'll show you how to calculate the answer. By the way, this is an unusual question, I think, for the Chem Regents. I haven't seen something like this. I can't even remember if I've ever seen anything like this. Well, if I go here to reference table A, I know that standard pressure in kilopascals, and I know it in atmospheres, and there's my conversion factor. 101.3 kilopascals is equal to an atmosphere. And I can use that, and I can either set up a fraction and cancel kilopascals and get to atmospheres, or set it up as a proportion and solve for atmospheres. This is the piece of information I need to have. What you see are two different ways to solve for exactly the same thing. In this proportion, I just set up kPa's over atmosphere, so 101.3 kPa's over 1 atmosphere, but I don't have 101.3. I have 116 over X. I'm going to cross multiply, and then I'm going to divide, and I'm going to get x is equal to, now on the calculator it's 1.145 and a whole bunch of other numbers. I would take it out at least one decimal. You could take it out a couple. It doesn't mention it in the question, so you're going to be fine no matter what. And then for using it as a conversion factor, that's this setup here, 116 kilopascals. I'm going to put kilopascals on the bottom. I want atmospheres in my answer. And what am I doing? I'm doing the exact same thing. I'm taking 116 and dividing by 101.3. All right, for 75, this is the answer key that the teachers would use when they went ahead and scored this test. And you see for 75, they're looking for 1.15 or any value from 1.14 to 1.16. They won't accept 1, obviously. They didn't accept just 1. So you would have had to take it out at least a couple of decimal spaces, even though it does not specify in the question. Just be aware of it. Don't just put down 1. Let's move on. For 76 through 78, we're looking at a reaction and some information. 76, on the labeled axes in your answer booklet, draw a potential energy diagram for the reaction represented by this equation. Well, potential energy diagram, right? We have potential energy and time. And what we have is an exothermic reaction. We're going to start high and we're going to end low. And don't forget, there's that activation energy in between. That would be acceptable for a potential energy diagram for an exothermic reaction. Moving on to 77, compare the activation energy of a catalyzed reaction to the activation energy of uncatalyzed. Let's use the potential energy diagram I drew for an example. When a catalyst is added to a reaction, it speeds it up. It speeds it up by lowering the activation energy. Watch the wording here in 77. The activation energy then for the catalyzed reaction is less than the activation energy for the uncatalyzed. Just watch your wording, like I said. Let's move on to 78. Determine the number of moles of O2 required to completely react with 28 moles of CO. Well, let's take a look at this. This is what we call a stoichiometric question. This is a mole-mole problem. They're fairly easy, but we do need the balanced equation. 28 moles of CO, so put the 28 above the balanced equation, the coefficient 2 underneath, and then the number of moles of oxygen, that's my X. What coefficient is front of O2 is 1. And now when I draw my lines, I have my proportion or my setup. See, it's a 2-to-1 ratio. So I have 28 over 2 is equal to X over 1. Now I can cross multiply and divide, or I know X over 1 is just X. 28 divided by 2 is 14. So it is 14 moles of O2. All right, 79 through 81. And by the way, you're doing great. If you've stuck with me this long, that is awesome. Just keep working hard. Maybe take a break if you need to and come on back. But here we are with 79. Identify the element in propene, that is in all organic compounds. Well, I didn't really need the propene in order to see this. And propene is right here. But the key is for all organic compounds, it is carbon. For 80, explain in terms of chemical bonds. So we got to watch that. Why the hydrocarbon reactant is classified as unsaturated. Well, my hydrocarbon reactant, that means hydrogens and carbons only, is here. That's that propene. It's unsaturated because it has one double bond. That's your answer, one double bond. And then finally in 81, write the general formula for the homologous series to which propene belongs. Homologous series, what in the heck? Remember, you have your reference tables. There are 3 organic chemistry reference tables. Homologous means that it's changing when I go from one member to the next by the same number of carbon atoms and the same number of hydrogens. All I have to do is look up the general formula for alkenes. We identified the type of group, if you will, for organic based on endings. That's all we got to do. Let's go there. I find table Q, and lo and behold, I have the word homologous, the ENE ending, and here is the general formula for alkenes. That's what I want to write down in the answer booklet for my answer. Moving on. You have made it to the end, 82 through 85. Great job. Here we have a reading passage. We're dealing with nuclear chem, talking about radioactivity and Geiger counters and gamma radiation. We have a little picture here showing up, and then we have questions. So let's go to the questions. Now, what's totally annoying is question 82 has nothing to do with nuclear chem. It's asking you to compare the ionization energy, the first ionization energy of argon to the first ionization energy of helium. The first ionization energy, it's the energy required to knock an electron out of an atom in its gas state. The first ionization energies are listed on reference table S. Now, you're given the names and not the symbols, but the names and the symbols are on reference table S. We want to look up argon. We want to look up helium, we'll compare the numbers, and we have 82 on our answer booklet. All right, I find helium. First ionization energy is here. We're talking 2372. Argon, element 18, it's here. Helium's first ionization energy is higher than argon's. Or you could say argon's is lower than helium. There's the answer. All you had to do was look it up. Let's move on. All right, for 83, we want to find evidence in the reading that gamma radiation has a greater penetrating power than alpha or beta radiation. It is a fact, that is true. But now we have to use the reading passage to support that statement. You read through it, maybe you read through it again. Take a look at the reading passage, see if you can't pull it out, and let me show you. The sentence here says that to detect gamma radiation, an aluminum shield can be placed over the probe window to keep the alpha and beta radiation from entering the probe. So, in other words, an aluminum shield blocks alpha and beta radiation, but the gamma goes right through. That's how you know that gamma radiation has a greater penetrating power from the reading passage. Let's go to the next one. Question 84, we want to determine the time required for a sample of cesium-137 to decay to only 1/8 of the original sample. So we're starting with the whole thing, and over time, it's decaying to another isotope. In the reading passage, we weren't given the half-life. That means we need to find it on the reference tables. Cesium-137 on reference table N, we find the half-life is 30.2 years. What does that mean? Cesium is decaying into a different isotope over time. Once we hit 30.2 years, now half of it, the 137, has decayed into something else, and it just keeps going. Then we would have a quarter of what we started with, and then finally an eighth. I'll show you on a table. The other thing is we're dealing with cesium-137 that decays by beta minus decay, and you're asked in the last question to fill in the missing isotope. Let's do both right now. I set it up typically on a chart, time and mass. We're starting at time 0. At time 0, you had the whole sample of cesium-137. Now, why am I using the number 1? Because we're going to go ahead and we're going to decay it until we get the fraction. 30.2 years is the half-life. Once we hit that 30.2 years, half of those atoms have decayed into something else, and the mass of the cesium-137 would be half of what it is. We go another 30.2 years for 60.4 years, and half of a half is 1/4. And then finally, half of a quarter is 1/8. And we have to add another 30.2. So that's going to be 90.6 years. That's the amount of time that has to go by in order to go from the whole sample to 1/8 of the original. For 85, you're asked to complete the nuclear equation in the booklet for the decay of cesium-137. Let me show you it here. Let's just clear this out. I have cesium-137. You may be given the atomic number, you may not. Of course, for isotopes, the number of neutrons can change, but the number of protons do not. All right, for cesium, we have 55 as the atomic number. With beta minus decay, if you take a look at reference table O, I forgot about reference table O, you see that the beta particles, you got a 0 for mass and a -1 for charge. If that's not on the answer booklet, you need to write that in. I also wanted to point this out to you anyway, that this is on the reference table. Now, the missing product. Well, what has to happen is my mass numbers on either side of the equation must equal out, and my atomic numbers. It's fairly easy to see, let me just change the color here, that 137 is equal to 0 plus 137. It's the bottom that sometimes messes up students. I have 55 on the left. What number am I going to have on the right? Well, whatever number it is, it's plus or minus 1. So be very careful. The answer is not 54, it's going to be 56. Because 56 minus 1 is equal to 55. Now, I have to identify the product. That means I got to go back to the periodic table and find element 56 and put in the symbol. Back to the periodic table, and element 56 is barium. I got to put my Ba in, and we are done. All right, it is official. Let me draw this in. Barium was our missing product. Actually, barium-137 to be exact. This ends Part C of the August 2019 Regents exam. You made it through the whole thing. Good job. Good for you. Keep working hard. Check out other videos. Work on other questions. Come on back and use my YouTube channel, NY Chem Coach, anytime you need it. And good luck.